My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 562. In this lecture, we will try to understand weight initialization in neural network. This is continuation of my previous lecture, that is lecture number 561. I request you to go through my previous lecture, that is lecture number 561, before understanding this lecture. Just let's assume all my weights has large negative numbers. Then what happens? Then there is other problem that we encounter. If all my weights are large negative numbers, my W transpose X, that is Z, assuming my X is pre-processed or data normalized. My X is the input. Let's assume it is already normalized. I discussed about data normalization in initial lectures. Please go through that particular lecture. What does normalization means? What does normalization means? It means that we have done mean centering and we have done variance scaling. Remember, this is data normalization. Data normalization is mandatory. You have to do it for any optimization problem, including back propagation and deep learning algorithms. Since X is normalized, X is not too large. As X is normalized, X is not too large or not too small, because you have done mean centering and variance scaling. You are already centered and scaled. So if W is large negative value, your W transpose X becomes large negative value. When Z is large negative value, just try to recall, if your F is ReLU, let me assume Z is a large negative value. Why? Because your weights are large negative, therefore your Z is large negative value. And if your as Z is large negative, just try to our recall ReLU function, isn't it? If your F is ReLU, F of Z becomes 0, isn't it? For Z, if Z is negative, your F of Z becomes 0. This is the problem with ReLUs. If your Z is large negative value, your F of Z becomes 0 for all of your activation units in the network. So you should again not have WKIJ. You should again not have WKIJ, which are the weights, as large negative numbers, isn't it? Why we are facing this problem? As WKIJ are large negative numbers. This is the problem even with sigmoid, isn't it? Yes, just try to just see F of Z is 0. If Z is large negative value, means we have problem with ReLU activation functions. If your Z is large value, F of Z becomes 0 for all activation units in the network. Even just consider your sigmoid activation unit, isn't it? Even with sigmoid, not just with ReLU, you have problem not only with ReLU, you have also problem with sigmoid activation function. Because how does sigmoid works? For large positive or negative values, you have the problem of vanishing gradient, isn't it? Vanishing gradient is a severe problem, isn't it? What does it mean? For large, it's not gradient is very small for large negative numbers or positive numbers in the case of sigmoid, isn't it? So what is the solution for this? So let's take our idea 1. What is the solution? Idea 1 is very simple idea. Our weight should be small, isn't it? Our weight should be small, not too small, not too large, isn't it? Not all 0, and there must be some variance. There must be some good variance. That's what we discussed. There must be some good variance among the weights. Let's take all the weights and compute the variance. Variance should be good enough. If the variance is high, what does it mean? There is lot of variability between your weights, isn't it? If variance is high, high means what? There is a lot of variability in between the heights, isn't it? If you have lot of variability, each of your model is going to get different inputs. Model means what here? Neurons, activation units. Hence, they learn different things. So, you need to have good variance within your weights. Next thing, given these constraints, what are the constraints here? First constraint is weight should be small, not too small, not too large. Second constraint, not all 0. Third constraint, good variance, isn't it? Given these constraints, one simple thing I can do, all my weights will come from normal distribution, isn't it? WKIJ is normal distribution with 0 mean and small variance. Sigma is small. It is a small standard deviation. It is very simple idea. This is called random initialization, which is Gaussian or normal initialization with a reasonable small sigma. Now, when your sigma is reasonably small, your weights now has, yes, your weights now has, first point is standard deviation of sigma, and second point is you have some positive values and some negative values, because you are centering with 0, normal distribution with 0 mean and sigma standard deviation. How does this distribution looks like? It centers on 0. It centers on 0. You have some positive value which are, you have some values which are negative, you have some values which are positive. Some of your weights will be positive and some of your weight will be negative, and you have reasonably good variance, not too small and not too large variance, isn't it? What people have done, people said, can we come up with a better initialization strategies? Isn't somehow so? With a lot of experiments, and of course some theory, lots of researchers have done lots of experiments. Of course, there is some theory behind them, isn't it? There is some theory behind them, but the theory is not very strong. It is a weak theory, but there are lots of very good experiments through which we can come up with better strategies on initialization in the last few years. So before we go into better strategies, let me explain you a couple of terms. There is a term called fan in and there is a term called fan out. Fan in, fan out are very interesting variables. Let me explain them. Suppose you have a neuron. Suppose you have an activation unit F, isn't it? Let's assume you get 4 inputs to this neuron and 2 outputs. Suppose this F is an activation unit and it could be anywhere. So this particular neuron could be anywhere in your neural network. So for this neuron, you have 4 inputs. How many inputs you have? 4 inputs and 2 outputs. For this given neuron, your fan in equal to 4 because it has 4 inputs. Because it has 4 inputs which are coming into your function. And into your function into your activation unit. The fan out for this is 2, isn't it? So fan in basically gives, what is fan in? Fan in basically given a neuron, given an activation, which is neuron or activation, which is the same thing, isn't it? The number of inputs to the neuron is called fan in and the number of outputs is called fan out. Now the people have done lot of research saying we should initialize the weights based on fan in and fan out. There is a lot of experimental data here. There is some theory, as I told you earlier. It is, of course, it's a weak theory and it's not very strong and solid. Let's go and understand a couple of options. The first technique is called uniform initialization. So in uniform initialization, which is simple Gaussian initialization with a reasonably small standard deviation, not too small, not too large. That's the idea one. What is not too weights should be small. This is idea one. Idea one is weight should be small, not too large, not all zero, good variance. This is known as idea one. That's what we discussed, isn't it? What is my idea two? Idea two is uniform initialization using fan-ins and fan-outs. I request all of you to go through this lecture. I will continue this particular lecture on weight initialization in neural networks in my next lecture also, that is in lecture number 563. Thank you very much.